we're just knocking these down like crazy. Like there's no tomorrow. You could put a check mark on that one, on that one, on that one, on that one, on that one. Oh, we haven't done that one yet, but I'll let you work on that one. Let me come back to this one and just well, let me do this one. Let me do one of these real quickly, just for fun. So from here, you could say that tangent theta is equal to plus or minus the square root of secant square theta minus 1. That's just from using the square root property from here, from this problem. Square property, in other words, this is a square. If you take the square root on the right hand side, plus or minus square root property, and that takes care of this famous one right here. So you could put a check mark on that one.
Papi?
Yes, these ones work the same way.
Papi?
Yes, mija?
What are we talking about?
What are we talking about? That's a great question. What in the world are we talking about? Someday I'll tell you. Alright. Before I go on to the next topic, I want to just show you something for fun. Tangent square theta plus 1 is equal to secant square theta.
About that?
No. Yes, we're talking about this. I just proved this using the triangles, right? Using the definition and working on each side separately. But if you remember, there are four ways that we looked at of proving things. What were the 4 ways that we looked at for proving things? Working on each side, tweaking it on a look at the graph, started with something amazingly creative. I want to, just for fun, tweak a known identity, just for the hell of it. So I want to prove this one more time. This is I'll call this second interpretation with a B minor flat. I'm just kidding, I don't know what I'm talking about. Second point of view, maybe? Second point of view. Yeah, that works. This time I will start with a known identity. I'll start with this. I know that sine squared theta plus cosine squared theta is equal to 1. This is known. Why? Because we just proved it earlier. By the way, all of them have a logical order to them. If I've already proven all of these, I can use them subsequently. In other words, if I have already proven that one, I can use it on the next problem. At any single step, you can use anything that you've already proven, but you should not use anything that you haven't proven. Don't use things. This is the future. This is the logical future. Do not use things from the future. Use things that you already know. Otherwise, you'll create circular arguments with very, very questionable logic foundations. Does that make sense? Use only things that you already know. Only identities you've already proven. So this one I've already proven. I don't have to abandon the equality. I already know it's equal because I already proved it. Now I can tweak it. Now here's a famous tweak for you. Came from afar and it carries with it great significance. Here's a famous tweak for you. I shall take the left side and I multiply 1 by 1 over cosine squared theta, and I will take the right hand side and also multiply by 1 over cosine squared theta. That's the cancellation law of multiplication, says I can multiply both sides by anything I want. The next step, I will distribute this. Show you. Do you guys know the distributive law? This gets distributed to that, and that gets distributed to that. It's famous. It's called the distributive law. You guys have seen it, right? Yes, I know. That gives you a sine square theta all over a cosine square theta plus a cosine square theta all over cosine square theta, and that's equal to 1 over cosine square theta. Stop me if I'm lying. This is just by using the distributive law. Now, this one means sine times sine. The bottom means cosine times cosine. And they're squared, so altogether that means the sine over cosine squared. This is equal to 1, and this is equal to 1 over cosine theta times 1 over cosine theta. This is just algebra. But look what happens here. Remember the exchange house? One of the previous identities that we proved was, and we can use because we've already proven it, this one over here. Every time I've got a tangent theta, I can exchange it for sine over cosine. And vice versa. Every time I've got a sine over cosine, I can exchange it for a tangent. So I've got a sine over cosine here. So what can I exchange that for? Hello? The tangent. 1 over cosine. What is a 1 over cosine? What can I exchange that for? A secant. So, based on previous identities that I've already proven, this becomes a tangent square theta plus 1, and that's equal to a secant square theta from previous identities. Now you see why they pay me? What did we just do? We proved exactly this identity by starting with, we proved it by something that we already knew, start with something we know, and then tweak it until we deliver the goods, until we take you to the promised land right here. I told you. And that was the second view, second way to prove this. Why? Because it's fun to understand things in many different ways. It's fun to generate creative ideas, different ways to look at the problem. That's why.
Papi,
Yes?
I gotta leave if we're talking about leaves.
Okay, we gotta leave in case we talk about leaves. Thanks. That's creative. So, any old chump can just memorize these things. To memorize them, there's no glory in that. The real glory is in understanding. Okay? Alright, so... Okay, so let me break it down for you. Or for me, anyways. So I can organize my thoughts. Look at all the things that we get from the famous Pythagoras identity. We get, for example, for every single angle that you can think about, for 45 degrees, 30 degrees, 12 degrees, 1,272 degrees, no matter what the degree is, if you take the cosine square plus the sine square of that angle, you get 1. That's the first thing it says about angles. Second thing it says is this exchange rate, that every time you've got a cosine square, you can exchange it for a 1 minus a sine square. Or in a fancy way, you can exchange it for this peanut butter and jelly sandwich. It should be the 1 minus the sine times the 1 plus the cosine. Sorry. 1 minus the sine times 1 plus sine. It also says from here, you could tweak it. You could tweak it the way we just did to derive every one of these. Every one of these can be derived by just tweaking the very first one. Okay? So the entire paragraph can be tweaked, can be gotten by tweaking this one. It says things about the peanut butter and jelly. Every one of these, every time you see this 1 minus the cosine square, you should be thinking conjugates. Every time you see this 1 minus sine square, you should be thinking conjugates. Every time you see this, you should be thinking conjugates. Everywhere conjugates. Huge idea. The other thing it says that I haven't gotten to is it says something about a previous homework assignment that sort of just snuck in there, and I never really talked about it much. But now, and you probably thought, oh, this guy is crazy. He's smoking something. What in the world is that homework doing here? But it was carefully, methodically planned for this moment. Now we can make so much more sense of that, and by having done that homework, we can make this homework a million times easier and more comprehensible. So I need to go back and talk about a previous homework, and at the same time talk about some non-famous identity. You know, today or this last few days we've talked so much about all these super famous identities, and never have I talked about some non-famous ones. Today we get a chance to do that. So let me talk about this previous homework assignment. In some homework assignment that you had a while back, you had an exercise like this. You had something like this. Suppose that you know that x squared plus y squared equals 1. And then it would ask you something like true or false. Is it true that x plus y squared is equal to 2x plus y? No, 2xy plus 1. Now let's revisit this problem. We have 4 ways of checking if something is true. Work on both sides, look at the graphs, blah. Let me look at both sides. Abandon the equality sign. Abandon the assumption that they're equal. They just work on each side separately. So if I work on this side, I'll get that this is x squared plus 2xy. This is just by foiling plus y squared. This is just by FOIL. But then I'm given this really important assumption that x squared plus y squared equals 1. So this x squared plus that y squared, how much is that equal to? This tells me that I can always assume that I would always be able to exchange an x squared plus y squared, exchange it for 1. So these two together can give me a 1, and so I have a 1. I'll have a 2xy, and I'll have a plus 1. This 1 comes from exchanging the x squared plus y squared for a 1. Now it's clear that they're equal. And when you first see this exercise, it seems kind of silly. It's interesting because it just helps you get started on the right mindset for proving identities. But it does something much, much deeper than that. It sets you up to prove the following problem. Now suppose somebody asks you to prove that, prove this identity. Cosine theta plus a sine theta. If you take the ratio of adjacent to hypotenuse plus the ratio of opposite hypotenuse and you square it, you get the same thing as twice times the ratio of adjacent to hypotenuse times the ratio of opposite to hypotenuse plus 1. Prove that. Then you think, whoa, 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 whoa. That looks kind of crazy. In fact, that's not any of my famous ones. It's not even on famous sheet. However, you know something special about sine and cosine. You know that we have proven already that cosine square theta plus sine square theta is equal to 1. We know that anytime we want to, we can exchange a cosine square plus a sine square of the same angle. We can exchange that for 1. So this is exactly the same problem as, well, not exactly the same. It's almost identical to this problem, but the only exception is that instead of x, you have cosine theta. Instead of y, you have sine theta. So the proof will go almost identical. When you FOIL this, you'll get, well, what do you get? You'll get a cosine square theta plus 2 sine theta cosine theta plus a sine square theta. And this is just by FOIL. And then we know that you can always exchange the cosine square and the sine square. When you take them to the exchange house, what can you exchange them by? For? You can always exchange them for a 1. So this becomes 2 sine theta cosine theta plus 1. And now you see they're identical. And so these two are equal. And there were several, or actually many homework problems like that back there. These problems are absolutely crucial. They are really non-famous identity disguised in terms of x's and y's, but they're really identities for sines and cosines because they have exactly this relationship that a cosine square plus a sine square is equal to 1. So every one of those problems that you did in that homework assignment is actually one of these problems in disguise. Okay, so let's take a look at this one. Similar example. Similar question. We check both sides, and so here's a way to try to attack this problem. Here on this side you've got x's alone, only x's, no y's. Here you've got x's and y's. If you're going to try to see if they're equal, you either have to add y's here or change these y's for x's. And so you think to yourself, hey, what's the exchange rate for the y's? How many x's can I get for my y's? And if we go with the assumption that x squared plus y squared equals 1, that means the exchange rate is every y squared, you can exchange it for 1 minus x squared. That's going to be the key right here. Since this is even, I can break it up like this. Look, this will be x to the 4th plus a y square. And I write it this way because I know how to exchange a y square. A y square is equal to a 1 minus x squared. So this becomes x to the 4th plus 1 minus x squared. That's the going rate for y squares, right? Every y square is a 1 minus x squared. And now I have that this is x to the 4th plus, I need to FOIL this, I have 1 minus 2 x squared plus x to the 4th. And that gives me a grand total of 2x to the 4ths minus 2x squares plus 1. Then I have to check, are these two the same or not? By this point, it's certain that they're equal, and we've proven it. And that was a homework problem from the introduction to identities, but it's more than that. Now, for today's lesson, it becomes a problem such as this. Determine whether or not cosine to the 4th theta plus a sine to the 4th theta is equal to 2 cosine square theta minus 2 cosine theta. Whoa. Let me review my notes. 2 cosine to the 4th. So this should be a 4 minus 2 cosine squared plus 1. Is that right? Cosine to the 4th minus 2x squared plus 1. So the proof of this would be exactly the same as the proof of this. All right? Your sine square, you know that you got sine to the 4th power, but you know that every time you've got every time you've got a sine square theta, there's a good exchange rate for sines. What can you exchange? Every sine square that you have, every time you've got a sine square, what can you exchange it for? A 1 minus a cosine square. So that takes us to this place then. This becomes cosine to the 4th theta plus 1 minus a cosine squared theta, quantity squared. By the way, you knew that you had to do something here. On this side you've got sines and cosines. On this side you only have cosines. So either you have to add some more sines here, or you have to take away these sines and turn them into cosines. Both ideas would work. Okay, so where am I here? This would be cosine to the 4th theta plus 1 minus 2 cosine squared theta plus cosine to the 4th theta. Together that gives me 2 cosine to the 4th theta minus 2 cosine squared theta plus 1. And now it's clear that they're equal, and that proves it. By the way, these identities are not famous at all. They're not on the famous sheet. The only thing they give you is just practice. Practice on proving identities. That's all they give you. Practice on tweaking a known identity, or practice on work on each side. That's what they're all about. Maybe we can finish off with one of these famous ones. Peanut butter and jelly problems. This right here looks like the peanut butter. This looks here like the jelly, so that already gives you a big hint. We're going to work on both sides. On this side, what you want to do is complete the sandwich. So the thing that would be missing here to turn this into something nice would be to multiply top and bottom by the conjugate. What would be the conjugate of 1 minus the sine square, or sine theta? The conjugate would be 1 plus sine theta. So I'll multiply that on the top and that on the bottom. Multiply top and bottom by that. On this one, 1 over 1 plus sine theta. The missing ingredient would be the 1 minus the sine theta. So I multiply top and bottom by 1 minus the sine theta. Okay? Not only that, but that gives you the same common denominator, so you can put these together. You've got two terms on the left, you only have one. Either you have to take this one and split it in two, or you have to take these two and put them into one if you're going to make them look the same. Capiche? So this becomes 1 plus a sine theta on the top. That becomes 1 minus a sine squared theta. I told you, together these two give you something nice. When you multiply the conjugates, what can you exchange a 1 minus a sine squared theta for? Should be automatic. Automatic. Every time you see a 1 minus a sine squared theta, you can exchange that for something nice. You can exchange that for cosine square. You don't believe me? What does it say right there? I told you, we proved it earlier. A 1 minus a sine square, you can always exchange it for a cosine square. You gotta know your exchange rates. This becomes 1 minus a sine theta all over 1 minus a sine square theta on the bottom. So on the top, you have the same denominator now, so we can add the fractions just by adding the tops. You got a positive sign, negative sign, there you go. So all you have is 2 over 1 minus a sine squared theta. And of course, this is famous, so I can exchange this for a cosine, so that gives me 2 over cosine squared theta. And of course, what is a secant? After all, the secant is just a inverted cosine, and so there you go. The two sides look, we've proven that they're equal. I told you. Non-famous identity. Famous idea. Work on each side. Famous idea. The idea of conjugates. Okay? Super famous. Alright. I think we should stop here. What do you guys think? Your turn. Super famous. Put the check marks.